stream. Hopefully, you guys actually got, number one, the notification that this is even happening. So probably no one's even going to watch this. Just to introduce myself, this is Anthony Volkman, and I'm the owner of Volkman. Sorry about that. Amplifier. It is a monoblock. It's dual one-out gauge inputs. As you can see very well, they are one-out. So positive, and then 2 for the negatives. So these 3 are the positives, and these 3 are the negatives, and then your remote terminals. Now, the problem with this amplifier currently, let's see if I can get this thing to move. I just cleaned this place up, so none of the tools about yet. The problem with this thing is there's ringing in the output stage for some reason, and I believe the problem, number one, capacitors are what is appearing to be faulty. They're what's causing a weird I don't really know output. This class, it is, think of it as FM, frequency modulation. So as you have your AC, have it all these, some of it's little, some of it is your bass boost and all that stuff and gain. But this right here is, sorry about that. No one contrary to does not necessarily mean USB amplifier. You obviously plug in the wall inch driver, I believe, or is it clear on the magnet. You can see the coil. I mean, it's really, really cool. Aside from that, it actually universal serial bus protocols, USB. So to get the audio and analog CA input, it actually uses a USB called a DAC, digital to analog converter, and I'll go over that in just a minute with these amplifiers, but it's different. What that does is it uses 1010. Now let's use that, but I'll go over that in just a minute. By that I mean it's binary, so anyone that knows about computers will know exactly what I'm talking about. But by that I mean it actually uses an IC that receives stream of data, and then it turns it into what's called a sinusoidal AC sine wave, which is called analog, which is sound. So you can actually play it to a speaker. Otherwise, it would just be, I'm not really sure, because the baud rate is probably 200, so they do much of anything besides just short your computer out. If you connect the data of your USB to a speaker, don't ever do that. So it does actually feed it to an analog amplifier in that model. In the Harman Kardon iSub, it is for Apple technology only, and it does have a TDA 39, I think I see in it. It's a 30-watt mono amplifier. It is very nice. It actually sounds really good. It does have an, but turns into an AC sine wave and then feeds it to an analog class AB amplifier stage. Now, this with an from your RCA plugins into your messages, my chat, all messages are visible. This is the first time I've ever done this, so I'm all the chat and all that stuff. Anyways, okay. So you start out with an analog signal. So you plug your analog, your RCA's Radio Corporation America stands for, into random knowledge, and it puts it into the, you're not going to get 4,500 watts of power from your input stage. No, it's not going to work. Plus, that's DC. So you start the car, ooh, now you're up to 14.7 from the alternator. Still, if you try and hook your car battery across the speaker, it will just catch on fire and screw shit up. So don't do that. I have again, don't do as I do. Unless you just like burning stuff up and, then having your entire shop stink. Because it will make your entire house stink. Burnt voice calls. It's awesome. Anyways, getting aside from the task. So first of all, it comes onto the PCB, and that stands for printed circuit board. And this is just a basic video, just anyone who wants to watch. And a video it's did. I highly recommend his channel. He is absolutely awesome. He has his own YouTube channel for rebuilding amplifiers. I do the same. He's from Canada. I believe me to it. I do not know your name, so I'm sorry if you're watching this. Don't get mad because I can't. I'm horrible with names. Seriously. This is kind of a more in-depth knowledge into his channel for anyone that's in between us and a beginner. I actually didn't watch the second part of his channel. I believe. Yeah, part 1. And I didn't watch part 2 because the storm came through. But I just decided to make my own video. I do have a business here in Missouri, and I do take PayPal and all that, but that's not what we're talking about. So what happens is when you bring your analog signal input, you cannot directly take your RCAs, your low-level signal input, a peak-to-peak voltage of maybe 2 volts, and that's if your head unit is really good. I think I cannot remember. Now, you cannot just take this and shoot it right to your gates. Now, a MOSFET stands for metal oxide field effect transistor. Now, a transistor is a switch. So just like this little switch here, right? So you have I am the gate. My finger is the gate. Well, that's almost an incorrect representation of that. Instead, the gate is the actual flipping, the actual armature. It's what's connection and the disconnection. The connection and disconnection. Unless it's a dual gate MOSFET. And you can go and research that on your own. That's for RF use. That's for my other extension of my business. Now, what happens is you have gate, drain, source. Gate, well, the gate. It's what turns it on and off. The source, or drain, drain, and your source. Just think of that as the power, the voltage will drain into the circuit, into your transistor. Now, then you have the source, and that's the source. That's where you'll be sourcing the power from. And in most Class A amplifiers, that's where the power is taken off of. And actually, they don't normally use MOSFETs. They normally use BJTs, bipolar junction transistor. And I actually use just very high-powered NPN and PNP transistors. And that's because you have what's called a dual rail power supply. So this is for the positive side, and this is for the negative side. More on that in just a few minutes. Now, in order for a MOSFET to turn on and off properly, you have to have a proper voltage bias, and you have to have a proper, I wouldn't say current source. I mean, you do have to have enough current to keep the voltage from dropping out, kind of like a low dropout regulator. If you have an LDO regulator, then that means that when you put your voltage into it, say I want 12 volts to be coming out of the regulator, so you can use like an LM317. I normally don't use linear. I do use linear for radio use because you don't get the switching noise from a switching power supply or a buck converter. Now, low dropout means that you can bring it from, I think it's 38 volts maximum, but if it's a low dropout, you can bring the voltage down within, I think, 200 millivolts. So if you want 12 volts output, the minimum voltage input to the regulator can be something like 12.5 volts. Now that's amazing, right? Well, not all regulators are built like that. Now MOSFETs kind of have to have the same thing for the gates. BJTs are more picky. They require current. They are a current-driven device. They require very little voltage, but they require a larger amount of current. You'll notice that if you go to BJTs and such, that's not a BJT, sorry. You'll notice that the drive resistors, otherwise known as base drive resistors or BDR, will be somewhere in the range of 10 ohms, 12. I've seen some in the range of 20 ohms. However, a MOSFET gate, a gate drive resistor or a GDR, I have seen them as low as 47 ohms, but as high as 150 ohms. And that's because they require very little current to drive. And that is why they're perfect for what's called digital use. Now, in digital terminology, digital is basically, in my own mind, I guess you could think of it as digital as an artificially generated waveform from an oscillator. Square wave, sawtooth, um, triangle, reverse sawtooth, ramp sawtooth, anything that is actually artificially generated that's not coming out of a wall outlet, which is AC, alternating current, and it goes. So think of this as the neutral line. So it goes positive, neutral, and then down to the negative rail. Neutral, positive, analog. It's gradually increasing and gradually decreasing. That is an analogous signal. These, in a Class D amplifier, do not get a direct analog signal. They get a square wave. And by that I mean, when you try and feed your RCA voltages, when you input signal into the amplifier, you will then be feeding the amplifier the gain controls and your crossover controls. Now, I haven't taken this amplifier apart all the way, as you can tell. I just got this in not too long ago, and I just ordered the caps and stuff. So as you can tell, I have started removing all the clips. I haven't removed all of them yet, and soon I'll take the entire PCB out, but that's not in this video. This is just so you can kind of see what happens inside one. Now, what a preamplifier does is really simple. It takes in a signal that's very low and it amplifies it, but not to speaker level output. I do not recommend just building a little preamplifier and trying driving a loudspeaker with it. Won't work. They also require what's called a buffer. And a buffer is a device that takes the lower, I mean, it's not really low level. It is, considering what you're wanting, but it just amplifies the signal enough to where you don't get a lot of noise introduction, and if it is built incorrectly, you will get noise injection. And that is one thing I really like about these RCAs, is they're actually grounded. It acts kind of as its own shield, so it helps to keep noise from getting inside the amplifier instead of those plastic things. I hate those things. They're total junk. They break, they're brittle. I never build an amplifier using those. I always build them with at least this type of design. And that's what I mean. Qubed really builds their stuff really nicely. So the preamplifier will take the signal, and it also acts sort of as a buffer for your head unit, because your head unit, its outputs cannot drive that all on its own. Number one, the voltage is not high enough. Also, when you connect it to that many MOSFETs, it will drop out. The voltage will drop too much, and the gates will not be turned on and off fully. And that's why a Class D amplifier is so efficient, but that is also why you lose sound quality. Now, I have a home studio, and I use... phone's ringing. Someone else will get it. And I use Class AB amplifiers. They're less efficient, but they have better sound quality. And if I really don't care about efficiency, I use Class A. Very poor efficiency, but awesome sound quality, and tube is even better. But going aside from that again, we're losing off topic. Your preamplifiers will take the signal in and step it up to where it can be processed without it being drained of its own power, pretty much. So a low-pass crossover, the light's not very good over there, but a low-pass crossover takes the full signal input, the full range, highs, lows, mids, everything, and only spits out low frequency, and in this case, sub-frequency ranges. And this, I believe, has what's called a subsonic filter, which removes these sub-frequencies that the human ear does not perceive. And that takes a lot of strain off of the amplifier, and it takes a lot of distortion out of your system, because your subs will be playing, let's say mine plays at 28 hertz. Well, if you're playing also 15 hertz with a lower frequency, which requires even more current, well, you can just filter that out. And that's also known as a bandpass filter. And a bandpass filter means that only a narrow band of frequencies is allowed to pass through to the amplifier section. Now, so far, the preamplifiers and the low-pass crossovers and all of that will all tie into pretty much any amplifier. Class D, Class AB, Class B, Class D, Class T, G, H, all of them. Now, also, it all depends on if it is actually digitally enhanced or not. This, I do not believe it is, because I don't see any microprocessors. The Alpines do, a lot of them do. In fact, there's an SIP. Huh, I didn't even know that thing was even there. Nice. Anyways, so what happens is you then have to turn your analog sine wave into a square wave. And that is what this board does. Now, this has what's called comparators, local oscillators, and buffers all on this one PCB. And that right now, D, or surface mount device, or even SMT, surface mount. And basically, all that means is they mount directly on top of the PCB instead of through a hole. Now, a lot of people, when they see that, they go, nope, screw that, I'm not working on this amplifier. Or they just think, nah, send it to someone else, or I'm not playing that game because it's too small. And I don't doubt you. Or blame you, I mean. Not one bit. I was that way until I went, it's fun. So, the reason it's SMD is not just for size. This is an IC, integrated circuit. All them little black things with the IC, with the multiple pins, are equivalency of those and those. Look how much smaller they are. Well, that's not just so that they're smaller. There's resistors, there's xenodiodes, I mean, there's everything on here to take the AC sine wave and turn it into a square wave. And I'll explain how it does that in just a few minutes. I'm sorry I don't have any like pen and paper, otherwise I'll do a very detailed description of how all of this works. And for some reason, no one is online. Sadness. What happens is you will get what's called parasitic capacitance and parasitic inductance. Now, that is a very, very big problem. Now, if you have, I use on this channel, didn't know I could do that. If you have what's called parasitic capacitance, what a local oscillator does is it uses what's called an RC timer. And in fact, this uses inductors as well. So if you have a voltage coming into a capacitor with an inductor, you will make what's called a LC tuned or an LC tank circuit. L for inductor, C for capacitor. Now what that creates is what's called a resonant frequency or a resonance, and that means that the capacitor will hold a charge. And when you cut the power, the capacitor will obviously discharge into the area of least resistance. Well, according to DC resistance, these are dead short. So the capacitor will discharge directly into here, which will make a magnetic field. Well, according to Lenz's law, the magnetic field generated will oppose the current input. So the voltage that will be generated when the voltage from the capacitor is depleted and goes fully into the inductor, it stores it kind of like a capacitor, but only in magnetism and not electrostatic plates. So that magnetic field will collapse right back in onto the inductor and make an opposing voltage that will go right back into the capacitor, and it will all happen again. Now, this is the output filter stage, so this is not how that's working. This is not for a resonant, this is not a timing circuit. This is to filter out the high frequency square wave, and I'll get onto that. Now, you'll have what's called a comparator, and you'll also have what's called a timer. Now, a local oscillator basically means you have a oscillator built into something to drive components, pretty much. So it's local. It's not an external oscillator. Now, when your signal comes in and it goes through all your phase adjustments and all of this stuff, it then goes into this board, which also is run by the dual rail power supply. And I'll get onto that in just a minute. But this is where people always ask me questions. This is why I'm making this long video. Now, you don't just turn an AC sine wave into a square wave by, you hear some people, well, you can use Zener diodes to try and clamp it, and you can use a specific type of diode rectifier or a wine bridge. No, that's not how you want to do that, because that's not necessarily turning to a square wave. That's called clipping. And you're just making the sine wave as it tries to go up. Think of the panel being the neutral again. As it's supposed to go smoothly up and smoothly down, the diode will allow only DC through. So it will allow the AC voltage as it's positive. But according to the output of the diode, it's just flat DC. Well, that's what a square wave is, yes, but that's not what you want at all, because you'd have to have two diodes so you could get both the positive and the negative peaks. Well, that's how a rectifier works for an AC sine wave, but this is not AC. Instead, your local oscillator will generate what's called a triangle wave. And it literally just looks like a triangle if you look at it on an oscilloscope. And I don't have the scope out now, otherwise I'd have a lot more going on here, and I don't have it hooked to power or anything right now. Now, a comparator which you can make out of yeah, I believe you can actually make it out of a 555 timer. In fact, the 555 is based off of a certain amount of comparators and a flip-flop. And you can go and watch Great Scott's videos about all that stuff. That's past this video. Now, what happens is you have two inputs. So the comparator will receive the triangle wave input on one input. Now, what a comparator does is, depending on the configuration, if the positive input has a lower voltage than the negative input, then it will go high. Now, if it's the opposite way around, if the positive input has a higher voltage than the lower voltage, it will shut off or will go low. Well, sounds a lot like Class D, doesn't it? Square wave, on, off, on, off, on, off. Now, it compares the triangle wave with the analog sine wave on the other input terminals. Now, again, this is a very simplified description, and I do not have any paperwork, so I don't get to actually show you what this looks like. Now, when that AC sine wave is going positive, well, the square wave is a set frequency. I mean, the triangle wave, sorry. And I've seen them all the way up into 45 kilohertz. Sometimes it's a 60 kilohertz. That's awfully high. But you want the frequency, it's called a carrier frequency. You want it to be well above human hearing range. Also, the higher frequency it is, the easier it is to filter it out. And this is called an LC low pass filter, unlike the active filters. Now, when you have the comparator getting a steady triangle wave input, and then you have your variance of your AC sine wave, that you're varying AC input, frequency, and amplitude for your base, you will get what's called a frequency modulated triangle wave. But on the output, it will be a square wave, because the comparator will say, okay, the sine wave is high, boom, and it goes fully on. And then it's on, and then when the sine wave goes low, boom, it's off, square wave. That's pretty much how it works. Now there's a bunch of feedback looping systems, and there's a bunch of, there are actually other oscillators that are built into the systems, and that is pretty much the simplistic, extremely simplistic basis of a Class D amplifier's driver. Now, the way that all of that is created is by using a dual rail power supply. And the reason it's called dual rail is because you have a plus and minus and then comms. So like a center tap transformer. So this would be ground, not amplifier ground, not the chassis ground. No, don't do that. I've seen so many people screw up amplifiers and they bring them in and they don't know what they did wrong. And it's because they just think, oh, I'll get more power and I'll just hook my speaker positive to the positive terminal and then the negative straight to the ground terminal. Don't ever do that. No, don't. That's why they have transformers. Now, the dual rail power supply means that it's isolated, and there are power supplies that are not isolated, but not for car amps like this. And so my amplifier I built has plus 200 volts and minus 200 volts, reference to COM. So rail to rail is 400 volts on the rails. That's a lot of voltage. Very deadly. That's why I say if you don't know what you're doing with car amplifiers or electronics in general, research. I'm not saying don't do it. By far, not saying that at all. Just research what you want to do, figure out what you want to do, and then go for it. And you'll always learn. So, now that that's out of the way, probably should have said that the first part of this video. Oops. You will have it's also known as a symmetrical power supply, or a split rail, or dual rail. Now, that dual rail is achieved by using these 4 transformers. And in the bigger amplifiers, it can use 6, it can use up to 8. I mean, I've seen it with 10 transformers before. Now, you'll see these 2 transistors here. Look kind of similar to that. Now, this is called a half bridge. And just a minute. I gotta find that thing again. Lost it. Oh, man. I swear, if my brain wasn't in my head, I'd lose it. Oh, here it is. Okay, so I'm going to show you one full side of the half bridge that drives this transformer. And that is done by, again, you saw this before, and then you pull hard. Right like that. Okay, really, really, really simple. You have 4 transistors. And like I said with what's called a dual rail power supply, the way to get a 12 volts in ground up to a very high voltage that is dual rail is to use a transformer. Now, what a transformer does is it's very similar to an inductor, but an inductor is when it just has one coil. A transformer is when it has a secondary coil in the presence of that primary. So you have a transformer. It transforms the voltage, and transformers will not run off of DC voltage. Now, if you go across the the drain and the source of this, you will have the battery voltage. You will. Because the battery voltage goes straight through the center tap. You'll see this is one side of the coil here. And then you have your let me think here. Wow, this has a dual wound primary. Okay. And then you have your center tap here. You can't really see it very well. Sorry about that. Then you have your second primary winding. And in all actuality, it's just one big primary, but with a center tap in it. Now, only one side of the primary is on at one time. And how the hell will that be done? Half bridge. Now, half bridge is a bridge of transistors that allow the voltage to be fluctuated in polarity back and forth through a load. Just like the half bridge on the output stage. And I'll go more into that in just a minute. Now, what happens with this is you have a second driver board. And this driver board is a local oscillator all in its switch mode power supply. And basically, that is also a type of switch mode power supply, but very different. It varies wave accordingly to the AC sine wave input. Now this, it doesn't have a reference like an AC signal from your audio inputs. It generates its own frequency and compensates for its own losses all on its own. That's what's called switch mode power supply. Now, a regulated switch mode power supply will mean that if the voltage on the input terminals volts, you will have, let's say, 300 volts. So plus or minus. Now, let's say that you have 14.1 volts. Well, you would think the voltage would be higher, right? Not necessarily. A truly regulated power supply will mean that no matter what the voltage input is, you will still have the same 300 volts, plus or minus 150 volts. And that's because it adjusts both the frequency and the duty cycle of the square wave. Now, I'm not going to go into very big detail on that because that takes all in its own time, its own data or video. Now, a square wave is fully on and fully off. No in between. It's digital, no analog, so it's more efficient. So these transistors are fully on and fully off. So actually, for a very short period of time, they're shorted. They really are. So the positive is shorted directly through the transformer, through one of the windings in the primary to ground. It is, but only for a very, very short amount of time. Now, when it starts to go backwards, think of this as one big transistor because both of those transistors are in parallel and both of these are in parallel. Now, both sets of grounds are connected to the same ground. There's no other ground because it's a single rail. It's just plus your battery voltage and then the negative. That's it. Just 12 volts ground. This is plus and minus and ground. So you have 150 plus 150 volts to common and then negative 150 volts. And that's how you get your AC sine wave so easily. Now, only one set of transistors is on, and that's why it's called a half bridge. This one's on, and that one's off. And then this one shuts off, and this one turns back. So the transformer voltage reference to the center tap will be going from this side to this side, this side to this side. And that's called a half bridge. So the power input does not change. It comes into the center tap. So the power is sitting of all of these power supplies, of all of these MOSFETs, including all of them for the rest of the power supply. Now, as this one is on, or dang it, my own finger keeps on getting in the way. Here, I got a better idea. As these two turn on, you will notice that people keep on messaging me that these will be off, and that's called and dead air at the point in time where these two are starting to shut down. These are not going to be on at all either. So there's a point in time where all four of these are off, where nothing is on, and that's called dead time control. That's where the square wave is not doing anything. Now, this also has a comparator in it as well, and it also has what's called a phase shift. So you have a high and a low output. That is not a dual rail output. That just means that you have, okay, here's a pretty good idea. You have a square wave, right? Well, so think of these tops of these transistors. I know this is really pathetic. I'm sorry. So think of this as a square wave as it moves up and then it goes down and then moves up and then goes down. Now, let's say you want those to turn on. Well, you shift the phase. You don't shift the polarity, you shift the phase. Now, do car audio, you'll know exactly. It means that you just say, okay, so this one's on, pulse, turn this one on, and then turn this one on, and then turn this one on. So you have a fluctuating voltage. Now, the secondary of the transformer is built the same exact way, and it has a secondary that is center tapped as well. So you get plus and minus voltages. And then it goes into your rectifiers. Now, I'm not going to undo those just because, I don't know. Yeah, screw it. I'll take it out. you have to be very careful when disconnecting these because it'll seem like you're breaking them, but when you're this close to the capacitors, you have to be careful that you don't push on them too hard as to where you're actually putting a lot of pressure on them, because then you'll snap them off the PCB. See, like that. You don't want to push on them. So I'll do that when I'm not holding the camera, sorry. And I'm just using my phone right now. So your rectifiers are diodes. So what happens there? Oh, shoot. Darn it. I just dropped that thing right in. There we go. Okay. So this is called a common anode and a common cathode rectifier. So these are not rectifiers, but these are exactly what those look like. They look just like that, well, more like those. A similar package. And these are not transistors. They do not turn on and off from an input signal. They have the transformer voltage inputs, the secondary outputs come in on the outer legs here. So it'll look, if you probe the outer legs, they'll just be shorted, but only because of the transformer. Now when it's on, the voltage is kind of like when you look at a triple phase. It'll be like, holy crap, a triple phase. Those transformers look like they'd be shorting each other out because only one of them is on at a time. Well, not necessarily. This is similar, but not exactly the same. So you'll have one side of the transformer will be positive. So let's say this is the common anode. So the positive voltage will come into the outer pins here. This thing is freaking out on me. Will come in here, but the diodes are arranged in a way to where they're pointing towards each other. So the two cathodes are pointed, they're contacting each other. Okay, so let me call them cathodes, sorry. But the positive voltage is what would exit. So when the transformer swings high, it will come through through the rectifier and out the center pin, and it'll charge your positive rail of your capacitors here. Now, at the same time, you have your negative rail, and it is also energized at the same time in a way, because the transformer, even though only one side of the winding is energized at a time, that same primary is energizing, but it's hitting all of the coils. So by that I mean, most people don't really think of it this way. Even though the transformer only has one of the primaries on, one of them is going to be positive here on the secondary, but the other secondary is getting that same magnetic field. So the other ooh, excuse me, sorry about that. Just a minute. Making a mess. Causing more problems than I'm solving. So by that I mean you will have the secondary, I don't know why I keep on saying that, the second side of the secondary, the opposing coil, the opposing winding, will also output a voltage as well. So that will feed through your positive diode as well, only when it's positive. But when it's negative, it's connected to the negative as well. So which will come through and charge your negative supply. Now, both coils are connected to both of the diodes. So it doesn't matter which side is high or low, they will be going through a diode to charge your capacitors. Now this is called a full bridge rectifier. And in essence, what a full bridge rectifier does is it takes the negative side and it flips it up and charges your capacitors. Now, if you look at a schematic, that terminology sounds like a pile of malarkey, because you will see the negative terminal of your diodes going to the negative of your capacitor. That is the case, but by what they mean of it flips it up is it receives both pulses. Like if it's your regular wall outlet, it receives both the positive and the negative portion of the sine wave. So you get the 120 hertz DC. If you have low filtering on your rectifier stage, you will see a 120 hertz positive bump only, but no negative. Now, a half-wave rectifier only uses one diode, and it only gets the positive side, the positive bumps of the AC sine wave, but it cuts off the negative entirely and just doesn't use it because there's no channel for that to go because the diode is only forward biased when the sine wave is positive. But when it's negative, it's like the diode's not even there, so it's like an open circuit unless your diode explodes, and then it's a very bad fire, and then you really, I don't want to talk about that. Anyways, you will have a 120 hertz bump. Now here, it's very different because these, I believe, are running at 35 kilohertz. So it runs 35,000 times a second. And that's per side. So this one's running, and this one, and this one, and it runs back and forth. Now, I know this probably doesn't seem like a very good example of how this actually works, but this is just because I have had a few requests for a basic terminology of how this all works. Now that you have what's called a dual rail power supply, after your PWM makes it, which also stands for pulse width modulation, and that's when you adjust the duty cycle of a square wave, which also happens here. Now that you have your proper dual rail power, the dual rail power supply sits across these two sets of transistors. Positive here, negative here. So on the drain of this one, the positive voltage sits. But however, on the source of these, the negative sits, because that's how it will be hooked up as a single MOSFET. Your gate, your drain is positive, your source is negative. So since it's dual rail, well, that's how you have to do it. Because if you connect the negative rail to the drain, just like you would here, if you're building like a regular class AB amplifier that uses PNP and NPN, they're already designed to have the collector, the base collector emitter, which is gate drain source if it's MOSFET. The negative will just go through and sit there just like as a in-channel MOSFET. Well, in Class C amplifiers, they do not use a in and a P channel. It's only in channel, which is very good because the differences between the in channel and the P channel characteristics are very different. They don't seem very different, but they are. You also have to have actual polarity phase shifts. It makes things a little more complex. But this is just as complex, but more, because of how it generates that square wave. Now, what happens here is you also get that phase shift for here, for that one set on, one set on, one set on, one set on. Well, these will be conducting at one point in time, and then these will be conducting at one point in time. And these are just the outputs, just like those. It's just their opposites. Focus. Focus. There. Now, lots of people would ask, well, why not just let them both come on? Well, that means it would just be a dead short because you have your positive rail, and then this is your center. So the part that has the negative sign is the voltage on the capacitor that's the negative side, the terminals, and then this positive. So this would be your center tap of your transformer, and that is where the center tap of the transformer goes on the secondary. And that's your ground for the power supply, not chassis ground. Can't stress that enough. So your drain of the positive side, this voltage sits right on it. However, on the opposing channel, the negative sits on it. Well, think of your drain here and your source here. Let's turn it both on. Bam. Shorts right through it. So no, cannot have that. And that's why Class D amplifiers are very, very complex, because they have to also have what's called dead time control to be absolutely positive that at absolutely no point in time that both of these are even the slightest of bit on at the same time. Now, that also improves efficiency because you don't get leakage, you don't get you do get some crossover distortion. And that's why people say that Class D doesn't sound as smooth, it doesn't sound as rich, and that's because it's actually reproducing the sound wave. So you're turning into an analog, you get your analog signal from your phone, which is actually a DAC, a digital analog converter, like I mentioned with a Harman Kardon, and it outputs this signal in an analog waveform. You filter it after you preamplify it, and you adjust your gain and your subsonic frequencies and all that, and then you feed into here that nice wave that is pure, nice, into a very harsh square wave. Well, if you feed a square wave to a speaker, you'll only make it mad because square wave is DC, but only for a short period of time. And like I mentioned before, it's something like frequency modulation radio. The frequency modulation means that you have, let's say, 92.5, guess the 92.5. That 92.5 is not just the name of the station. I've had so many people ask me that. It's actually the carrier frequency that that station is running at, which is 92.5 megahertz. Well, this doesn't run in the megahertz range, but you understand what I mean. So you have an, oh yeah, analog signal, and then you have your whatever you want to do with it when it's transmitting, when it's your radio, you want all your sound effects. So let's leave this out of that. And then you have that. That's pretty much what FM is. And it's called PLL, phase lock loop. And that's to make sure that you don't get a phase variance when your carrier wave is what is sending out at 92.5 megahertz. That's how you can have it on, but you don't even have to play music, but you don't get static because it's sending out signal. So your antenna picks it up and it's quiet because it's blanketing it. Well, same thing here. It actually will pick up that it will receive a wave, if you want to think of that, of the square wave. But that square wave has already been modulated, just like in radio. You modulate the signal that is going to go to your antenna with the audio signal. And it looks something like if you have your oscilloscope and square wave will increase in width. It does not increase in frequency. It increases in width, both pulse. PLL means it makes sure that the frequency does not change, also doesn't change phase. And that is not the same for this, not really. Now, when you're talking about Class D tech, have the you have that harsh square wave run into the gates. But that's why it's so efficient, because they don't get a very AC sine wave. They get a boom, on, boom, off, boom, on, boom, off, boom, 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 boom. And then it is fed to the gates, and they output that at a very high voltage because it has a very high voltage bank amplifier. Now, these are the relays, and this is called your short protection and all that stuff. So you'll notice when you turn the sample on, you'll hear click, and that's these turning on and off. Disconnect terminals through these direct contact wires through the relays to the corresponding polarity. Now the inductors are connected to these MOSFETs. The MOSFETs are not connected directly to the output, unlike a Class AB amplifier, which actually uses resistors, and that's just for load balancing, and that's because no two components are exactly the same. Nothing is perfect. No filter is perfect either. And that's why Class D amplifiers sound a little bit different. So what happens is, you don't want that harsh square wave coming through. So you build a low pass crossover. Now, also, it's technically a DAC, a digital analog converter. You're taking a digital square wave, on, off, on, off, on, off, on, off, on, off, and you feed it through the inductor, and I'll tell you exactly how this works in just a minute. And it outputs I guess I could say pure. I mean, I wouldn't say it's very, very pure. There is some oscillation still present. I mean, if it's built very nicely, you will probably notice hardly nothing at all, even when you're looking at an oscilloscope. But there is still some there. And that's why over here you have what's called correction. You'll actually see what's called Zener diodes and even a transistor, which will send a signal back to here to say, okay, there is this in the signal, or it has dropped, and that's to increase your dampening factor. And Class D amplifiers have a very high dampening factor, and that simply means, kind of like them low dropout voltage regulators, or the gates, when you have this thing, I think I put 102 volts, I think, 102 volts on the output rail, on the output terminals. When you hook a load to it, that's 1 ohm. Well, what's going to happen when you hook 1 ohm to 100 volts? It's going to be like, bam, it's going to short out, right? Well, not really, because you have what's called an inductance. And that's why these are called inductors. And the speaker is inductance. It's inductive. It has a voice coil. And this is a voice coil. This is out of a Rockford Fosgate 10-inch punch sub. This is a dual voice coil. As you can see, it's had a rough life. This is my demonstration coil. And it's dual voice coil, so it's got 2 voice coils in the same coil. And again, for people that do car audio, this video is probably lame as heck, but this isn't funny. But this is an inductor. It has copper wire. Well, according to Lenz's law, again, when you push an electrical current through a wire, even if it is DC, it will. Now, an inductor resists or it impedes. You have resistance for DC voltage, impedance for AC voltages, or alternating, or pulsing, whatever. Anything besides DC is impedance. And that's also where you have ESR, equivalent series resistance with capacitors. And they also have their own inductance as well. That's called parasitic inductance, but that's, sorry. You will have the square wave coming in to the inductor, into the input of it, I guess you could say. Now, this is not a transformer. There's only one winding. It may look like there's more than one, but there's not. There's only one. And as that square wave is alternating, or it's very, very high speed, that's how low-pass crossover works. A inductor impedes the instantaneous change of current, while a capacitor impedes the instantaneous change of voltage. So these will allow low frequencies to impede high frequencies. And by that I mean allergies. As the high frequency comes in, that high frequency is going to try and get through it. But think of a resistor. The squiggly lines on the schematics? Yeah. So the electron has to try and, instead of, well, same thing here, but via magnetism. And the inductance of it being wrapped around a coil also helps. But if you read the resistance, the DC resistance across these with a multimeter, it'll be 0. It will be in the sub-ohm, but according to those, it will be a short. Well, but for a high frequency, it will be very high impedance in the kiloohm, in the tens of kiloohms range. So where does all that power go? Magnetism. So as the voltage goes through the wire, it generates a magnetic field around it. Well, obviously it's going to be very strong because it's in a core. It's called a toroidal core. And this is a toroidal transformer, toroidal inductor. Now you don't have to have toroidal core inductors. You can have different ones as well. So as you have the voltage, come on, focus. There we go. As you have the voltage, the high frequency coming in, it's going to make a very high-powered magnetic field. But since it cannot charge instantly, it's going to impede that flow of that high frequency. However, the low frequency, which is a higher current, will flow right through it. But the voltage, which is high frequency, won't pass through it. Now, obviously, like I said, no filter is perfect. This is a very simplified description. Although, wow, this is a 55-minute video and nobody has commented. This is sad. Anyways, you will still have some AC, some of that high frequency getting through. Now, that is why you have these. There we go. These are capacitors. Now think of that as these as the two ends of this there. See that? So they're really, really close together. So if they weren't shorted together, that would be a capacitor. That's called an air capacitor or an air plate cap. Now that's used for very high voltages, stuff like that. These, they're microns close to each other, but they have a dielectric in there. And these are propylene, I believe. I can't remember. I just ordered them not too long ago, and I can't remember. Long day. So what you have is plates that are very, very close together, so they don't allow very high current through, but they allow very high voltage or high frequencies through. And that's how you make low-pass crossovers for audio that's not Class D. You will see those crossovers for like component speaker systems, and the inductors may look more like this, or they may even look, oh, I have one here. Here you go. This is the Memphis two-way crossover. This right here is an inductor, cap. And then here, I believe, is a varistor. And then this is a bulb. This is the bulb fuse for the tweeter. Now, a high-pass crossover means that the capacitor is running right after the MOSFETs, and the inductor is after the capacitor. Now, they don't run in series of each other. The inductor, accordingly to the circuit, is directly in series with this to the output terminals, while the capacitor is in parallel with the inductor output directly. Why? See, there's two of them in each side. This is the COM, this is the negative. Now, on this is a full bridge amplifier, and then this would be its own. Now, I don't believe it's a full bridge because there's only two, and I have seen full bridge amps that only have two inductors. However, this I do believe is a half bridge. So going away from that, just the simplistic terms, you have the high frequency impeded by this, but whatever gets through will, I guess you could say, capacitively short through the capacitor. But the low frequency that's going to your speakers, to your speaker wiring, to your speaker terminals, will ride right over the capacitor as it's not even there. And that's how it works. And for you to simply swap it around, you put your capacitor in series with the MOSFETs, and the cap will be, it'll be MOSFET, cap, wire. That's a very simple crossover. Better design. MOSFET inductor with the output of the capacitor to the ground of this. Even if it is run off of a single rail power supply, it will go to what is named ground or COM. That's where it will go, like the LM386. Very simple, runs straight to ground, unless you're running a dual of this. Now, the reason, even when it's high pass, the reason you would think, well, this is very low resistance, well, that's because it has a very high impedance, and the high frequency will ride right over it to there. But since you don't want it to ride over it, you want it to block it, so the low frequencies will go through it. But when it's a high pass crossover, the high frequencies will go through the caps, and they will ride over the inductor, but the low frequencies that are still able to get through the capacitor will short, really basically short to ground. And that's why your inductors have to be very precisely tuned, and your capacitors. If it is improperly done, they will get very hot, and you can damage your amplifiers and you can damage your speakers. So either know what you're doing or don't try and do that. Now, building an amplifier can be even more daunting, obviously, because you have to think of all of this. And I haven't even gone over everything at all, like how the low voltage for the preamps is achieved because these do actually run off of a dual rail power supply as well, just like this. Ooh, excuse me. Just much lower voltage. Normally plus and minus 15 volts. So you get 30 volt swing. And my amplifiers very high powered, but run at, so it's a little 6 volts difference. But these are, if I'm correct, yeah, those are your voltage inputs. But signing off. Enjoy the night. Like, comment, and subscribe.